Welcome to my lab report on modeling a falling object using gravity and drag for Physics 2211. My name is Yuvraj Dedwal. Let's get started. All right, so an introduction. The purpose of this lab is to compare and contrast the effects of drag on falling objects and also create a model to predict the motion of a falling object. So we've got a couple of ground rules here. Acceleration due to gravity is equal to negative 9.8 meters per second squared. Your weight force is going to be equal to the mass times your acceleration due to gravity times the unit vector 0, negative 1, 0. Okay, and this is the force that's pulling your object downwards. And then we've also got our drag force, which is the scalar speed squared times the drag constant times the velocity unit vector times negative 1. And that's because your drag force will always be pointing in the direction opposite of your velocity. And in this case, the drag force will be pointing up. A couple of spoilers. Our drag force model was far superior than our just pure gravity model. And we will discuss why that is in the future. All right, so some assumptions for this is that the only two forces that are affecting the falling object is the gravity and the drag force. There may be some other forces that are affecting the falling objects, but we are not considering them for this model. And we are also assuming that the falling object is falling in a 2D plane rather than a 3D space, which is not entirely true, but it's close enough to be true, so it works out. And again, we are modeling this motion with the equations for gravity and drag that are mentioned in the previous slide. All right, so some initial conditions. We've got our system, which is the falling object. In this case, it's paper, and the surroundings, which is going to be just Earth. We've got the mass of the paper, which is about 1.93 grams. We got our position, which is essentially 0, 0. And yeah. All right, let's go watch the video. So in the video, you can see that we are starting from up here, and our paper is starting from rest. And we drop it, and it comes down. And yeah, we've found our point masses. And yeah, that's about it. Cool. Moving forward. So how are we going to predict this? So if we have just gravity only, we can just set our weight force equal to the mass of the ball times the acceleration due to gravity times just negative the unit vector with negative 1. And we can also set our force net just to be equal to weight, because in this case, we are just looking at the weight force only due to gravity. And then we've got our ball velocity formula, velocity update formula, and we've got our position update formula. Simple enough. Pretty straightforward, similar to the last lab. And for our gravity and drag model, we are going to be modeling using the equation of the magnitude of the velocity squared times the drag constant times just the unit vector 0, 1, 0. And we are adding that to our weight to create a net force. And that is what we'll be using for our velocity update. And yeah, that's about it. And we chose our drag constant to be 0.003, and that is just due to trial and error. All right, moving forward. So compare and contrast. When we graph all these out, we can see that our prediction that we just used plainly gravity for is quite off from our actual what it turns out to be. And this shows that the only force that is affecting this object is not just gravity. It's got to be some other force. So when we put in the predicted for gravity and drag, it turns out that, hey, it's pretty damn close to what we actually found. And that shows that there's probably two forces acting on this object, both gravity and drag. All right, so now moving on, what is terminal velocity? Well, terminal velocity is when the net force acting on the object is 0 newtons. And the model that displays terminal velocity is the gravity plus drag model, because in this model, you've got two forces that are acting in opposite directions that cancel each other out. And as you can see, over time, at about past half a second, your acceleration, which is the change in velocity over time, is decreasing significantly to the point where it's almost 0, which means that the net force is almost 0 because your net force is equal to mass times acceleration. All right, so what if we were to, instead of dropping the piece of paper from a rest position to throwing it down with initial velocity of -5 meters per second? Well, we see that even if we drop it at such a fast speed, the speed of the paper slows down eventually to negative 2.5 meters per second, regardless of its initial velocity. And it was also in the previous slide, you can see that it also ended up at negative 2.5 meters per second. So you can see that your terminal velocity remains the same regardless of speed. And so in conclusion, we found that the drag model was far better at modeling out the falling object motion. And this suggests that there's both weight and drag force affecting the object. And we also found that terminal velocity is not dependent on initial velocity. Thank you so much.